Hello, everyone. My name is William Sosrapartono, and I'm here with Ashok Chakravarti today to present on the topic of parallel techniques in image processing. So, to give a brief introduction, what exactly is digital image processing? So, digital image processing is the processing of a digital image by a computer, and it is essentially the process of enhancing and extracting information from an image. As you can see with the example on the right, the original image is not as informative as a process image, and it goes through some digital image processing and goes through several filters and algorithms to lead up to the process image, which can be interpreted better. And interest in digital image processing stems from two principal application areas. This being the improvement of pictorial information for human interpretation, as well as processing of scene data for autonomous machine perception. So in the latter application, interest focuses on procedures for extracting from an image information in a form suitable for computer processing. Essentially, this means that the latter half of the application area is essentially trying to make computers see. So it can recognize certain elements in the picture that it's analyzing. So an example of this would be automatic character recognition, industrial machine vision for product assembly and inspection, military reconnaissance, automatic processing of fingerprints, and etc. So what exactly is a digital image? So an image actually refers to a 2D light intensity function f of x and y, where x and y denotes spatial coordinates, and the value of f at any point essentially is the brightness or gray levels at that point. And these are arranged in such a way that it's essentially an array of pixels. So f of y, f of x, and y that has been discredited both in spatial coordinates and brightness. And you can see this is sort of how an image is laid out, or the pixels are laid out in the example below. So to say some digital image basics, to be suitable for computer processing, an image f of x and y must be digitalized both spatially and in amplitude. Digitization of the spatial coordinates x and y is also called image sampling. Amplitude digitization is called gray level quantization. And because of the amount of pixels, the storage and processing requirements increase rapidly along with the spatial resolution and the number of gray levels. So an example of this is a 256 gray level image size of 256 by 256 occupies about 64 kilobytes of memory. And images of low spatial resolution produce a checkerboard effect. So to go over through the process of an image, it starts with image acquisition, which is the acquiring of image from an external source. Image generation, which is the generating of images from a digital source. Image compression, which is the data compression applied to images to reduce costs for storage and transmission. Image manipulation, which is the altering of photos to improve ability to extract information. Image analysis, which is the extracting of meaningful information from images, mainly from digital images by the means of digital image processing. Image display, which is the output of processing, essentially how is an image displayed. Image perception, how an image is perceived. And digital image processing is essentially the green highlighted portions, and it revolves mainly around image compression, manipulation, and analysis. So for image compression, it is essentially trying to retain a lot of the original quality of the photos while being much smaller in file size. So the image is decompressed mathematically identically to the original one without loss in quality. And a lot famous formats include GIF and WinZip, and it uses the LZ algorithm in order to do this. So as you can see with this picture on the right, when you zoom in, there is a loss in quality when you compare the two. However, when you actually compare the images, there's the images in totality, there's actually a very subtle difference, but it's not noticeable. So there's not a serious loss in quality. However, you can also see that the file sizes are also very different. So one is 8.9 megabytes and the other is 68 kilobytes. So this is another example of image manipulation, which is deblurring. So several filters and algorithms are applied to the image, and it improves the quality and ability to extract information from the image. This is another example of image manipulation, which is noise removal, where it applies a filtering, so it removes a lot of the noise in the image. This is an example of image analysis, which is edge detection. And this is an example of a real-life application of image analysis, which is the medical application, where it can detect changes in the eye. This is an example of image analysis for another medical example, which is checking for differences in the teeth structure. And this is another example of image analysis for biometric image matching. As you can see, these two are very similar fingerprints. However, they are different. And this is one of the ways that digital image processing can help with one of its applications. So to explain why digital image processing is used, for compression, image data needs to be accessed at different times or locations. And it's also used because we have limited storage space and limited transmission bandwidth. Image manipulation is used, and it might experience non-ideal acquisition, transmission, or display. It is also used because it might contain sensitive content, so that's in order to fight against piracy or forgery. It also is used to produce images with artistic effects, such as pointillism. And image analysis is used in order to reduce the burden of human operators and also to essentially teach a computer to see an AI task. So just to ask, how much computation does a single image take to process? So to give an example of simply copying an image, each pixel has around 24 bit values for RGB. And for an image processing program requiring 200 operations per pixel, a processor must provide a computational power of over 30 giga operations per second to process the full HD color images at 24 FPS. So if you look at the amount of computation that this requires, it's really difficult for a general purpose CPU to provide enough computational power to operate complex vision in real time. So this drives the need for more computational power. Computer vision tasks, which aims to make a computer understand and see, are extremely sophisticated. There are many algorithms that are in place in order to detect elements in the actual environment. So consequently, computer vision systems usually require a large amount of computational power because of these two reasons. So firstly, like I said, lots of complex algorithms are needed in order to run the computer vision system. So this includes counting the amount of people in the frames, recognizing certain elements like windows, buildings, cars. And also secondly, because immediate reactions are almost needed, as most computer tasks require to be processed in real time. So 24 FPS for surveillance camera and 1000 FPS for analyzing events, which are too fast to see. So a solution to actually improve image processing is to have very advanced computer parts and architectures. And a solution to this is actually parallel and distributed computing at a very large scale. So to go over parallel computing, there are actually two types of parallelism in digital image processing. One such type is task level parallelism, which is multiple tasks that are independent, are processed separately by multiple processors. And typically modern CPUs have multiple independent cores to operate different tasks. And this type of parallelism is actually exploited by the multiple instruction, multiple data architecture, which is the MIMD architecture. And the other type of parallelism is the data level parallelism, where it's a large amount of data needing to be processed by a single algorithm, and it's actually processed by multiple processors. So this is exploited by the single instruction multiple data SIMD architecture, and this is the actual type of parallelism that is used in digital image processing. So to go over the MIMD architecture, so MIMD stands for multiple instruction, multiple data. It's the most straightforward and most popular parallel architecture. It includes a set of n individual processors, as you can see with the example on the right. And there are actually different types of MIMD architectures, which I will go over in the slides ahead. And it has the ability to process different instructions on different data simultaneously. And in other words, the processing cores have the ability to process multiple tasks at the same time. And the system is designed to exploit task level parallelism. So going over one of the architectures is actually shared MIMD architecture. So it is a group of memory modules and processors, and any processor is able to directly access any memory module by means of an interconnection network. And the group of memory modules outlines a universal address space that is shared between the processors. And however, shared memory module may create problems such as synchronization and memory protection that need to be addressed. The main disadvantage of this is that there is a lack of scalability due to contention to access a similar memory module. And the winner actually accesses the memory while losers have to wait. And the higher the number of processors, the higher the hardware complexity, which leads to the greater probability of memory contention. So distributed memory MIMD architecture is another architecture of the MIMD architecture. And here, it clones memory processing pairs, which is known as a processing element, and links them by an interconnection network. So essentially, each processor is paired up with its own memory. And each processing element can communicate with others by sending messages. And by providing every processor with its own memory, the distributed memory architecture bypasses the downside of the shared memory architecture. And a processor may only access the memory that is directly connected to it. So it can achieve high implementation in a multi-computer. Special attention must be paid to load balancing. Although recently much research effort has been devoted to automatic mapping and load balancing in many systems, it is still the responsibility of the user to partition the code and data among the processing elements. So the next architecture is actually the SIMD architecture, which is the single instruction multiple data architecture. The SIMD architecture aims to exploit the parallelism only at a data level by executing the same instruction on multiple data streams simultaneously. So because all the processing elements or PEs share the same instruction at the same time, SIMD processors have a significantly lower hardware complexity than MIMD processors. And SIMD processors can afford to contain much more performance elements than MIMD processors, which results in significant speed improvements when exploiting data level parallelism. And another difference between MIMD and SIMD is that SIMD has a single decoder while MIMD has multiple decoders. So modern GPUs actually have SIMD architecture in them, and this is exemplified by the CUDA architecture by NVIDIA. And CUDA stands for Compute Unified Device Architecture. And so a modern GPU is a processor array which accelerates graphics processing speed by using SIMD parallel computation mode. And GPUs specialize in highly data parallel computation, and CPU is almost necessary for most algorithms. So the actual issue with CUDA by NVIDIA is that it's very difficult because the GPU requires the CPU. The latency between those two actually becomes a bottleneck, and that's one of the cons of the CUDA architecture. So although the CUDA GPUs provide significantly higher peak performance when processing highly parallel data, comparing with CPUs, they have their own drawbacks. This, of course, is the communication latency. So if the performance gain obtained by the parallel computation on GPUs is not big enough to compensate the overall communication latency, processing the algorithm on GPUs is slower than processing the algorithm on CPUs. So ideally, GPUs favor algorithms that have the maximum amount of data parallel computations and minimum communication between the CPU and the GPU during the processing stage. So an example of this is training neural networks. So I want to give an example of image processing in pixel parallel mode. So generally speaking, most image processing systems have the potential of partly being implemented on a SIMD CPU and increasing the processing speed by exploiting pixel level parallelism. An example of this is the mean filter. So this essentially is just having a kernel applied to a pixel and having it averaged out so that the filter can, each pixel can be similar to each other through averaging it. So it's essentially just a simple filter to smooth images. So the algorithm of the mean filter is replacing each pixel value using the mean value of its neighbors, including itself. So an average kernel is used here on the bottom right. So if the 3x3 mean filter is used to smooth an image with a resolution of n by n, the pseudocode for the traditional sequential this is the pseudocode for the traditional sequential CPU. Each pixel itself and its neighbors are added together and then divided by 9. So as you can see, this is the pseudocode for implementing this the filtering. So it goes through each pixel and actually adds up the it actually multiplies it and then adds up every single pixel and then divides it by 9, and then it is then applied to the pixel in the middle. So after this, going through the parallel processing of images, we can see that parallel processing on images is actually quite parallel. So essentially what the CPU does is that it splits up the image into, it scatters the image into two parts, and then it has a sequential operation on each partial image, where it is then combined together to form the final image. And this is just one of the functions, or this is just a simple filtering that is operated on the image.
Hello everyone. So I'll be talking about image segmentation algorithms and how we can parallelize them. Image segmentation is one of the many image processing algorithms. It is mainly used to reduce the original image data content for further processing or faster processing of the image. So image segmentation basically partitions the input image domain into regions. So these regions will contain pixels with a certain similar property with respect to each other in that particular region. It is widely used in many applications such as medical imaging, robotic vision, and face detection. So, as we all know, with the development of higher resolution imaging technology in these areas, the sizes of image data are growing rapidly, and so therefore, this will require longer processing time if the conventional image segmentation methods or algorithms are used. So there are many algorithms to implement image segmentation. The two main popular and widely used ones are watershed transform algorithm and k-means clustering algorithm. These two algorithms are parallelized to address the issues of slow processing of images when used a conventional image segmentation method. So first we look at the watershed transform method. Watershed uh, watershed transform is a popular image segmentation algorithm, especially in medical image analysis. So it basically partitions an image into valleys of pixels with brings that are shared by adjacent valleys, and these brings are called watershed lines. However, this being a popular algorithm, it also has a drawback called over segmentation. So this occurs when the image has many tiny valleys, which causes the watershed algorithm to over partition the image. So so therefore the resulted image can contain a dense collection of regions, and this might distort the important features in the original image. A parallel watershed is a parallel watershed transform algorithm is typically implemented on a cellular neural network, which is also called CNN, and this is a universal machine. So transform can be parallelized without considering the problems such as synchronization, communication, and load balancing. And this is because of the CNN's massively parallel array computing ability. Now let's look at the implementation of the watershed transform by immersion for grayscale images specifically. So to understand the idea of watershed by immersion, you can you can imagine a landscape with catchment basins being immersed in a lake, and also imagine that a hole is pierced at the local minimum of each catchment basins. And now the water will fill up at the basins start with the local minimum. Also, dams are built at points where water is coming from different basins would meet. So finally, when the water reaches the highest altitude in the landscape, the immersion process is stopped. So as a result, the landscape is partitioned into regions separated by dams, which are called watershed lines, and can also be called as watersheds. So we can imagine these grayscale images as such landscapes made of pixels with various altitudes, 0 to 255. So this can produce a binary image by watershed transform, where one black is assigned to dams and or watersheds, and 0 white is assigned to regions that are surrounded by dams. There are two major classifications of current parallel implementations of the watershed transform algorithm. So one is domain decomposition and the other is functional decomposition. We are only going to cover domain decomposition in this presentation since it is widely used and the most popular one among the two. So the idea of domain decomposition is that it divides the image into sub-images and distributes them across processors. And each of these processors uses the sequential algorithm to process its assigned sub-image. So it is domain decomposition can be much more portable than functional decomposition. This is because that one domain decomposition result of an image can be used for many algorithms if they're processing the same image. There are also two dominant parallel programming models that we use throughout the presentation, which is message passing programming model and shared memory programming model. In message passing programming model, tasks and data are assigned to processors, and the processors interact with each other by initiating an explicit communication calls. So whereas in the shared memory model, all the processors share a common memory and the processors interact with each other by simply reading and writing to the shared memory space. So we achieve the parallelization of the watershed algorithm by dividing the input image matrix into p strips of submatrices. P is the number of processors, and each of these processors will be applying watershed to one submatrix. So in other words, it can be said as every processor runs the same program but processes the different data. Also, the data allocation is done statically before the runtime. This is because dividing the image into strips of columns than the number of rows, it is due to the smaller quantity of the columns rather than the rows. So the frequency of communication is little bit smaller than dividing the image into slice of rows. As the image shows, 0, 1, 2 will be the strips of the image divided, and p minus 2, p minus 1, p will be the processors. We also take advantage of the barriers in the during the parallelization. So they are basically used in the parallel program to synchronize all the processors and make sure no one gets too far ahead of the other process. So they so this causes so barriers also introduce the overhead, and this is natural because but they are necessary to ensure the correctness in the final result. So this image depicts the parallelization of the watershed algorithm, which are the steps involved to parallelize the watershed algorithm. So as you can see, only the step 3 and step 4, which are initialize output image and immersion steps, are parallelized in the algorithm. Step 1 and step 5 are not parallelized because they are execution times and they can be assumed to be negligible. And the step 2, which is to find minimum and maximum altitudes, is not parallelized because two global shared variables are used to store the minimum and maximum altitudes of the pixels. And these are the results obtained after parallelizing the watershed algorithm. So in this example, we use a 300 into 300 grayscale image used to test the performance of the parallel watershed algorithm. The segmented image is produced when six processors are used. This is the image, and this is the graph. Here we have time on the here this graph compares the time taken for the processor to process the image. As we can observe that as more number of processors are used, yeah, the processing takes much less time. Now coming to the second algorithm, which is k-means clustering. So this algorithm clusters the image dataset into k subsets of pixels, and each subset will have a center value that is the average of all pixels in the subset. So therefore k subsets resulted in k total centers. So a pixel is grouped into a subset by first calculating the distance between the pixel and each center, and then the pixel is grouped into the same subset that has the closest center. So after this, one passes through the image, error is calculated, and the clustering process is stopped when the error converges to a value. Here error is the sum of squared distances between all pixels in a subset and the subset center. Let's look at the clustering algorithm itself. So these are the steps involved in the algorithm. So to begin with, we read the image file, which is a text file, and store the image data in a matrix array. Then we find the maximum and the minimum pixel values of the input image. Then we initialize k centers with the results from step 2. Then we calculate for each pixel its distance to center and cluster the pixel into the subset that has the closest center. Then we calculate the k centers. Each new k center will be the average of all pixel values in its subset, and then calculate the new error, and then the sum of square distances between all pixels in a subset and the subset center. Then we repeat the steps from 4 to 6 until the error is converged to a value, and finally write the output image to an image file. So in k-means clustering, for a color image, it reduces its original number of colors to k colors, whereas in a grayscale image, it reduces its original 256 possible levels down to k levels. So as a result, this causes k-means to effectively reduce the information content of an image while preserving its important features. As you can see, the image that has a sequential k-means is preserving its important features. Parallel k-means clustering algorithm. So the image shows the steps involved in parallelization of the k-means clustering algorithm. So the implementation of the parallel k-means clustering algorithm will be similar to the watershed transform algorithm. The input image is again being partitioned into p strips, where p is the number of processors, and distribute them over p processors. Here, as you can see, only the clustering step is parallelized because it will dominate the total program execution time. So in clustering, the sum of all pixels in a subset and the total number of pixels are used to calculate new centers. So there is a shared memory locations are allocated to store these values, and any processor can update the sum of subset by adding a pixel to it, and therefore lock is used to prevent processors from writing to the same memory location at the same time. To look at the results, to get the results, a Marvel machine is used to conduct the experiments and quantify the performance of parallel k-means clustering algorithm. The images produced by both sequential and parallel k-means, as you can see, are almost the same. The performance of the parallel k-means is shown while the clustering process appears to have a linear speedup. There is a speedup in the execution time which is linear. So when more processors are used, more contention would result because more processors would try to write to the same memory location at the same time or simultaneously. The performance analysis of the optimized parallel k-means can show good scalability and is almost and with almost negligible overhead. Also, it is close to the linear speedup, which is achieved by optimizing the parallel k-means clustering algorithm. And this concludes our presentation. So these are our references, and thank you for watching.